Good morning, or depending on when you're watching this, good afternoon, good evening, or good night. I'm your Calc 1 instructor, and today we will be looking at definite integrals. Now, over the past couple of days, we have begun looking at the problem of area, specifically the problem of area under a curve. We looked at how to approximate such areas by adding up a bunch of rectangles, what we refer to as a Riemann sum, and we define the area under a curve as the limit of these Riemann sums, as the width of the rectangles goes to 0, and the number of rectangles we are adding together goes to infinity. Now, the main idea of the definite integral is just that the definition of area can be extended. Namely, it can be extended to functions that may be negative. In other words, so far, area under a curve has meant that the area between a curve y equals f of x and the x-axis, where f of x is always greater than or equal to 0. But what if f of x is less than 0? Well, it turns out that we can do essentially the same thing. So what follows is going to very closely mirror the slides that I put up for the previous section. So we let f be a continuous function that is defined on the closed interval from a to b, and we divide a to b into n subintervals, x0 to x1, x1 to x2, x2 to x3, all the way up to the nth subinterval from x sub n minus 1 to xn, where here x0 is just a, the leftmost endpoint, and b is xn, the rightmost endpoint. All of these subintervals have equal length, delta x, which remember is b minus a over n. And then what we do is we let x sub I star just be arbitrary sample points, numbers that live in the ith subinterval. So you'll pick some x sub 1 star that is between x0 and x1. You'll pick an x2 star that's between x1 and x2, and so on and so forth. And remember, what we do is we look at sums that look like this. We take a summation from I equals 1 to n of f of x sub I star multiplied by delta x. And remember that what this was giving us is a sum of rectangles. F of x sub I star is going to give you the height of the rectangle, and delta x is the width of the rectangle. And we called these summations Riemann sums. And so note the only thing that's different here is that now this f of x sub I star that we're multiplying by could be negative. So it's not really the height of rectangles, it's really giving us a height that is negative in some cases, which is kind of weird, but we'll see what this ends up looking like later. So then, we define the definite integral as the limit, as n goes to infinity, of these Riemann sums. And we denote it with this little squiggle going from a to b of f of x dx, provided, of course, that this limit exists. Note again that this definition of the definite integral is the same as the definition of area under the curve from the last section, except we are not assuming that f of x is positive. Before we look at some examples and see how this definition plays out, let's look at some other integral terminology. Haha. First off, to calculate an integral as to integrate, if the limit that defines the integral exists, then we say that f is integrable. This very much parallels the idea of differentiable. Remember, a function is differentiable if the limit that defines the derivative exists. This weird squiggle here is called the integral sign, and note that it looks like an elongated capital S because the integral is a limit of summations. The function f of x that we are integrating is known as the integrand. The numbers a and b are called the limits of integration, namely they are called the lower limit and upper limit, respectively. These define on what interval we are looking at. Finally, the dx here, which corresponds to the delta x in the Riemann sum, is not an actual term that we multiply by, but rather just something that indicates that x is the independent variable, that we are integrating with respect to x as opposed to some other variable. This distinction will become relevant when we get to section 5.5. Now that we have our terminology out of the way, let's look at how this definition of the definite integral relates to the area under a curve. Again, if the function f of x we are integrating is non-negative, then these two are the same. Otherwise, If f of x is possibly negative, then the definite integral represents the net area between the curve of f and the x-axis, and the Riemann sum approximates this net area. And what do we mean by net area? The integral from a to b of f of x dx is a1 minus a2, where a1 is all of the area that is above the x-axis, and a2 is the area below it. Remember that both areas are still trapped between the curve of f and the x-axis. Here is a visual example where f of x is sometimes positive, but sometimes negative. On the right, we see that the area above the x-axis is viewed as positive area, while the area below the x-axis is viewed as negative area. So despite all the area under this curve that we see from a to b, integrating f of x over this interval would actually result in a number close to 0, because there is roughly as much positive area as there is negative area. Like matter and antimatter, they annihilate each other, if you will. Looking at the Riemann sum on the left, we can see why the area below the x-axis is negative. Remember, the rectangles all have width delta x, which is positive, times f of x sub I star. And so where f is negative, that height in a loose sense, is actually going to be a negative number. So the areas of those rectangles is going to be negative. Therefore, approximating integrals, the bulk of the homework for this section, is essentially the same as approximating areas as in section 5.1. You will just naturally have some numbers that are negative once you plug into your function f of x. Now let's finally look at an example where we use geometry to evaluate integrals. The graph of g consists of two straight lines and a semicircle. We will use that to evaluate each integral. The first is the integral from 0 to 2. Remember that this is just the net area under the curve from x equals 0 to x equals 2, or just this area here. This is just a triangle with base 2 and height 4, so the area is going to be 1/2 base times height, or 4. Now let's evaluate the integral of g of x from x equals 2 to x equals 6, which here is going to be this semicircle, which you'll note has radius 2. The area of a semicircle is 1/2 pi r squared, so with radius 2, that is 1/2 times 4 pi, or 2 pi. However, since the semicircle lies below the x-axis, it is considered negative area, so our answer for this integral is actually going to be negative 2 pi. Finally, we want to integrate g of x from 0 to 7. So in other words, we want this entire net area. So we're going to have the triangle over here, as well as the semicircle, as well as this tiny triangle. Note that this tiny triangle here has a base and height of both 1, so its area is 1/2. So this integral is going to be 4 minus 2 pi plus 1/2, or just 4.5 minus 2 pi. Now, important questions to consider are these. When is a function integrable? And how do you integrate when you don't have nice geometric shapes? As it turns out, being integrable is a much weaker condition than being differentiable. An integrable function doesn't even need to be continuous. The condition that we will use is this theorem from the textbook, which states that any continuous function is integrable, as is any function f with only a finite number of jump discontinuities. In truth, even more functions are integrable, but this is good enough for us. As far as how to evaluate integrals, at the moment we only have one option, to use the definition of the integral as the limit of Riemann sums, where for calculation purposes we substitute b minus a over n for delta x, and a plus I times delta x for x sub I. As you can well imagine, this is not an easy process, much like how difficult it was to differentiate using only the limit definition of the derivative. How to do this, though, will be the focus of our lessons tomorrow. Until then, adieu.